Imagine this. You're walking along with your young cousin Bobby, when all of a sudden you notice that his eyes roll up to the back of his head, he loses control of his limbs, and he slams to the ground. Bobby has just had his first seizure. What is a seizure? A seizure occurs when the normal electrical communication between cells in the brain goes into hyperactive mode. And having multiple seizures leads to the disorder that we call epilepsy. Now, epilepsy can be thought of as a sort of raging thunderstorm in the brain when there's constant electrical discharges of activity that become uncontrollable. Unfortunately, Bobby's not alone. There's more than 5 million people who suffer from epilepsy around the world. So how do we treat these people with epilepsy? Well, currently, we either prescribe anti-epileptic drugs or we perform seizures. These are two other common methods. Unfortunately, as you can imagine, both of these treatments focus on treating the symptoms and not the underlying disorder. So how is it then that we can focus and shift our research into looking at prevention rather than treatment? This is where my thesis comes in. My name is Elvis Cela, and I'm interested in what makes the healthy brain become epileptic in the first place. How does the initial activity between cells, which allows normal cell communication, become overactive and lead to seizures? The way that we answer this is by establishing a new model of epilepsy in animals. And the way we do this is that we make a specific subpopulation of cells in the brain sensitive to light. After these cells are sensitive to light, we then use light over many days to stimulate these cells and drive them to seizures. Our model has two advantages over current models of epilepsy. The first is that using light prevents damage to the brain from actually causing the seizures. And the second advantage is that our model allows tracking and following specific cell populations in the brain. So coupled together, what we have found using our model is that when you induce seizures in the brain, once they start, they don't stop. Our research so far further suggests that this may be due to some rewiring between these specific cells which we are stimulating with light. Our next step is to investigate exactly how the rewiring is changing during seizures. And I think this is important because fundamentally, if we want to understand epilepsy, we have to understand how the disease arises in the first place. This is so we can help Bobby and the millions of sufferers around the world by preventing the disease in the first place instead of treating the symptoms. Thank you.